Just a quick video with a few extra details about floating point if you're interested. This stuff, I think it's important for you guys to know, but again, the full details will be in another video. This is how the single, short, and double long representations are set up. The exponent for the short is 2 to the 7 minus 1, or sorry, the bias for the exponent, okay, none of that matters. The important thing here is the range of values. So for a single precision or a short floating point number that's 32 bits long, you can get a number that's sort of plus or minus 3.4 times 10 to the 38. That's the size of number you can get, and you can get negative 38, positive 38 for the exponents, but that's sort of the range of values. And for the double precision, it's around 1.8 times 10 to the 308. And again, plus or minus that, plus or minus the exponent, that's the range of these things. There are 23 binary bits of significand in the short one and 52 binary bits of significand in the long run. And there are all sorts of extra features, like a couple bits are reserved for rounding percentages. There are, I think, 8 bits preserved for the exponent, 1 bit for the sign, 11 bits for the exponent in the bigger one. And so each of these sort of features gives you some precision and some idea of the range and limitations of these floating point numbers. So if you're not doing anything anywhere close to 10 to the power of 38, don't use a double precision long. And if you are needing more than, but you should use it if you're needing more than 23 bits of precision, which you probably wouldn't need. 23 binary bits of precision, I think equates to about 10 bits of digital precision, which is plenty, right? You don't need it's plenty for most things. You don't need super high precision unless you're doing really high precision stuff. So if you need high exponents or high precision, use double format. But for most cases, a regular single format should be plenty of precision. And a 32-bit floating point number is significantly easier to deal with than a 64-bit floating point number, as you will see. If you want to do math with floating point numbers, this is what it looks like. First, you have to unpack every bit into those 3 fields, right? The sign, the exponent, and the significand. And just like an RGB value has red, green, blue, and the alpha channel, you split them up into pieces, and we showed you how to do that using shifts and masks and stuff. So that's the first step. You have to do that. You have to unpack everything with shifts and masks and get those 3 separate values. Then, if you want to add these 2 numbers together, first you have to check their signs to see if you're actually adding or subtracting. Then you have to check their exponents to see if each bit means the same value, because if the exponents are different, the values of the bits are different. Then if the exponents are different, you have to subtract them to see how much they're different, and then shift around the significand so that the values actually line up. Then you can do the addition or subtraction or whatever, and then you have to see if that result changes the end result of the exponent by 1 bit, right? You might carry over to 1 bit bigger, 1 bit smaller, and then repack everything up and put the result back together again. It is a very complicated and difficult process. And again, I'm not expecting you to build a floating point math machine, but I do expect you to know that it's complicated and know why you should preference integers if you can. A lot of bad things can happen when using floating point numbers. If you subtract 2 floating point numbers that are very similar, you can lose a whole bunch of precision. And that's a problem, right? If you want to compare 2 floating point numbers for equality, it may be that they're different at the 10th bit. And you have to then say how similar is similar enough, right? Integers have to be exactly the same, but floating point numbers have to be only mostly the same. So if you're comparing floating point numbers for equality, you can't just subtract them and say, is it equal to 0? You have to subtract them and say, is it less than some epsilon? Right? Everything involving floating point numbers includes some sort of error. This is one of the ways that we actually make random numbers, is we add and subtract floating point numbers and allow this error to creep in, and that error is usually somewhat unpredictable, and you can get nice, reasonable pseudorandom numbers that way. So yeah, if the numbers are close together, you may lose precision. You have to find some way to verify whether the result fits in the representation. And it isn't just an exclusive OR gate. There's a lot of extra logic you have to do to verify things like overflow, verify if the result is a true 0, then you have to represent it as a special number. If the result is not a number because you're dividing by 0, or if the number is too big for the representation, and so you say that it's infinity, or whatever, right? All of these things are special cases that have to be verified in logic. And in most cases, you don't verify that in hardware. You actually verify that at a higher level in software. The operating system, the floating point processor unit does all this kind of stuff. It's really complicated and difficult. Lots of work to do. You have to have logic for multiplication and division as well. As it turns out, multiplying and dividing is easier in floating point numbers than adding and subtracting floating point numbers. They're both harder than multiplying and dividing integers. But if you had the choice, if you had two floating point numbers and you had to do something with them, it's better to multiply or divide than it is to add or subtract. It's easier, as it turns out, which is somewhat ironic. So these are some of the challenges of floating point numbers. Once you get fractional representations, you get an expectation from the user that the numbers you represent are exactly correct, right? How do you represent the number pi perfectly? You can't. You can't represent it as a rational number, but you can be good enough for any practical purpose. There's somewhere, you can look it up, somewhere it says how many digits of precision of pi do you need to measure the diameter of the universe within a millimeter. And I don't think it's a lot. I think it's like 10 or 20 or something like that. So all of these people who memorize pi out to 100 digits, I mean, good for you, but it's completely useless in terms of real world practical applications. Same with even like 1/3. The number 1/3 does not have a valid representation inside a computer. 1/4 does, right? But 1/3 does not, even though in base 10, 1/3 is a perfectly good number. There are some numbers that are rational in base 10, but irrational, or non-repeating anyway, in base 2, and vice versa. So it's worth sort of paying attention to that. Again, a lot of that stuff is for the next course. So you can represent some numbers and they may not be representable. You can do a computation with numbers that are perfectly representable and the result can't be represented, right? You can have, so that's like 1 divided by 3. You don't get the right answer. You can have what we call catastrophic cancellation, which is a fancy word for getting rid of all of the significant digits. If you have two numbers that are very precise, right? Precise up to 6 or 7 bits of precision, and you subtract them, you lose all of that, and now you're down to 1 bit of precision because all the zeros before a number and all the zeros after a number don't count. It's how many significant digits you have access to, and now you only have 1, right? And then again, this is what I talked about before, comparing is problematic, so don't subtract, instead use the difference less than some epsilon. So these are some of the challenges and problems with floating point numbers. You're used to using them in your high-level languages, but it's worth knowing that they're definitely problematic. In general, in the past, well, yeah, in general, computers have used a coprocessor for floating point. Nowadays, GPUs are pretty popular for floating point numbers. A lot of machines will have a floating point pipeline in parallel with their integer pipeline and their load store pipelines, and so it's sort of integrated now into the cores of most machines, but MIPS does it with a coprocessor, and we'll look at how exactly that does that in the next video.